This is lesson 8-2, so we're continuing our handout for chapter 8, and you will need what's called a T-chart. So we'll be using a T-chart instead of a Z-chart. You can find those beginning in 8-2 homework, or I've posted a copy in the module, so you may want to pause and print that out. Now remember, in 8-1 I kept emphasizing that we knew sigma. Well, in real life, you're not going to know sigma, the population standard deviation. If you knew that, that would mean you knew everything about the population to begin with. So why did we do 8-1? That was just a transition from something we knew from chapter 7 into confidence intervals. Now let's look at a real situation where we don't know sigma. So what we're going to use is what's called student's T distribution. So we're going to be using T instead of Z. Why is it called students? Is because the person that came up with it was a student at the time and could not get credit in his name. And so the T formula looks a lot like Z. You notice we have X bar minus mu. Now here, instead of sigma, which again, we really wouldn't know in real life, we have sample standard deviation. And that's going to be a formula that we've already done before. So we'll either need to be given that or given individual values of a sample to find that over the square root of n. In our T statistic, we're going to need to also know the degrees of freedom. So if you look at a chart, the T chart, it has something called degrees of freedom here on the left, and it goes from 1 to 100. The degrees of freedom are your n value minus 1. And the other thing we'll need is the upper tail area. So we're going to be using this blue part here, these numbers, not these up here. So I've got those circled, the upper tail area. Now the distribution, T distribution, is very similar to our standardized normal, which is our Z. Both distributions are symmetrical and bell-shaped, and the mean and median will equal 0. As the sample size and degrees of freedoms increases, S becomes a better estimate of sigma. To find the critical values of T, again, we'll use the T table. Our degrees of freedom, again, are on the left, and our upper tail area are the columns. Okay, let's just look at this first simple example. We're just reading the T chart. We have a sample size of 16, and so our degrees of freedom are going to be n minus 1. That's 15 degrees of freedom, so we're looking right here. Now, our upper tail area, we're finding T at alpha over 2. Alpha for 95%, 1 minus 0.95 is 0.05 over 2, which is 0.025. So we go here, and we go down here, and we find the value 2.1315. You might find I have different things circled here because I've been using this chart for a while. So 2.1315. Let's do some more here. Okay, n is 54. Our degrees of freedom would be 53. And alpha would be 0.05. So we're finding T at alpha over 2, which is going to be T at 0.025 again. So we're going to that column, and we're going to go down to 53. So we'll need to get our other chart. This has 2 pages to it. And so the degrees of freedom is 53. There we go. We go over to 0.025. We get 2.0057. Now you might want to pause the video and see if you can find these and then come back to it. Okay, here our alpha is 0.10. We have T at 0.10 over 2, which is an upper tail area of 0.05, and we're going to go down to 62 degrees of freedom. So let's see what we say, 0.05, which is going to be here, and we're going down to 62, and that's 1.6698. And then for my other one here, that's t at 0.01 over 2. That's t at 0.005 with degrees of freedom of 17. And we'll flip back up to our other one. And here we go. So what we say, 0.005, 0.005, down here to 17, degrees of freedom, 2.8982. Okay, now that we know we can find those, here's our formula for our confidence interval. It looks very similar to what we did in 8.1. Okay, so we have a random sample of n equal 25, x bar is 50, s is 8, and we're finding a 99% confidence interval for mu. So mu is going to be x bar plus or minus. Now we have to find this t value, and again, unlike our z value, we could write down basically for 90%, 95%, 99% confidence interval. These degrees of freedom are going to be different every time, so we're going to have to look up t every time. Remember, we're looking at t at 0.01 over 2. Alpha is 100% minus that. That's t at 0.005, so we go to that column, and we're looking for 24 degrees of freedom, so 0.005, 24 degrees of freedom. We're looking at 2.7969. And that's times s, and they give us that as 8, over the square root of n. And we calculate that. I got my decimal as 4.475, and my confidence interval is 50 plus that, and then 50 minus that value. So in simplest terms, I'm 99% confident that my population mean is between these values based on my information from my sample. Okay, so we have another one here about commuting. It says, according to research, more than 85% of adults commute by car. Well, that part's not important. Sometimes we get extra information that we don't need, so don't be confused by that. We have a sample of 30. That sample yielded this sample mean and this sample standard deviation, and we're doing a 90% confidence interval. So we're finding t at 0.10 over 2. And again, I challenge you to see if you can find these first. Remember, we're looking at 29 degrees of freedom. So that was 0.05, 29 degrees of freedom, 1.6991. And so my confidence interval is going to be x bar plus or minus my t-score, and that's times, I've got the sample standard deviation, and that's over the square root of n, and I'll just write my values down. I think we've got that part by now. Okay, so we're looking at mu being between 24.855, a little messy there, and 31.085 minutes based on this average time of commute. And again, this is about the average time of commute, not how many adults commute. Now, in this next one here, we're missing some information. Notice that we're not given X bar, so we'll need to find that. We're given the individual numbers in the sample. So X bar, if we add these up, we get 41 over 7, and I'm just going to write that as 5.86. Now, we're also not given S. We had two formulas for S from a previous lesson. That was lesson 3.2. And I have one I prefer. You may prefer the other form. I like to use this form here. You take the sum of the squares minus the sum of the x's and then square them over n and then divide that by n minus 1, and that's all under a square root. So I'm going to make a little chart. I'll write all my x's down and their squares. My numbers in the sampler 1, 2, 3, 4, 5, 6, and 20. When I square, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. Now the sum of my x's is 41. Again, that's where I got that there. My sum of my squares is 491. So to set up this formula, it's the sum of the squares, 491, and I'm going to put all this under a square root in just a minute. Then 41 squared, the sum of all the x's, and then square over n, which is 7, and all that's over n, take away 1, and under the square root. When I calculate that and rounded, I got 6.466, okay? We need one more thing before we use the formula. We need t at alpha over 2. Alpha is 0.05. We're looking at t at 0.05 over 2, which is t at 0.025. And so we need to go to the 0.025 column and 6 degrees of freedom. 0.025, 6 degrees of freedom. That's 2.4469. And so mu is 5.86, the sample average, plus or minus our t-score, times our sample standard deviation over 7. And then let's go ahead and do some in-between calculations. That's plus or minus. And let's go ahead and figure out what all of this right here is. So 2.4469 times 6.466 divided by 7. Oop, I did forget the square root. Okay, I'm gonna go back and make sure I'm doing my formula correctly. I had forgotten my square root right here. So let me take the square root and then hit enter, okay. That's 5.86 plus or minus 5.98, okay. And that would give me a value, let's see, plus 5.86, 11.84, and then 5.86 minus 5.98, negative 0.12. And that would be my confidence interval there.